this video, we're going to talk about confidence intervals. We've been talking about how to calculate the probability that a value is greater than, less than, or in between certain things. Well, a confidence interval gives us a range of values that is likely to contain the true value. Think about wherever you take a sample. If you take a sample and you want the mean of that actual population, you haven't gotten the entire population, you just have a sample. And so what we want to do is we want to create an interval, a range of numbers that we think it's actually between, the mean is actually between, or the standard deviation is actually between these two values for the entire population. We're having to base this off of information that we know, so we're having to base this off of sample mean or sample standard deviation. But we want to come up with this confidence interval to identify where the mean should be between. So we come up with what we call a level of confidence. For a level of confidence, the larger the level of confidence, say that we're 99% sure that it's between the two numbers. Well, the more confident we are, the larger that range or that interval has to be. Because if I don't have to be that accurate, my interval can be smaller. But the more accurate that I want to be, I'm just estimating, so I have to increase that interval. A point estimate is a single number that is used to estimate the value of an unknown parameter. Remember, parameters are talking about the population. We very rarely ever get an actual parameter, so we have to estimate that. So x bar, our sample mean, is a good point estimate for our population mean. That's the same thing as S, our sample standard deviation, is a good point estimate for our population standard deviation. P hat, which is our sample proportion, is a good point estimate for our population proportion. Because we're estimating whenever we're talking about samples, we're trying to see if they actually fall within a value for our population. So we have to estimate based on these particular point estimates. We want to look at what we call our margin of error. Our margin of error is the largest distance from the point estimate to a confidence interval we'll cover. So this margin of error is how far below and how far above are we going to include from this point estimate. When we look at this, a capital M is usually used for a point estimate. Now we have what we also call a critical value. A critical value is the z-score that bounds the middle percentage of the area under the curve. So we're talking about the middle because we can have values on either side. So let's look at our normal curve. When we look at our normal curve, our confidence interval will be between these two values. So the z-score that goes here and goes here are going to be our critical values. Those are our cutoff points for this middle portion here. Now recall that the z-score or the standard normal or the bell-shaped curve is symmetric. So if I draw a dividing line here and I flip it over, this z-score is the negative, this z-score is the positive of that same value. So let's look at if I want 95% of my data in the center. So if I want 95% in the center, we'll remember that our common critical values or our common z-scores give us the value here or in the little bitty tail. So if I want this middle part to be 95, this outer part is going to be 1 minus 0.95. Remember changing the percentage into a decimal. I'm going to divide that by 2 because I have a part over here and a part over here. So I'm going to take 1 minus 0.95 and divide it by 2, which gives me a 0.0250 in here. A 0.0250 goes in here. This is our proportion and everything. So let's go back over to our cumulative normal table. And okay, here we are. Recall that this area right here is 0.0250. So that's our proportion, that's our percentage, our probability, which means it's going to be somewhere in this center part of the table here. So I'm going to go down and I'm going to look for 0.02. Okay, I'm somewhere around here. Here's 0.0250. And so I need to find that z-score. I'm going to follow it out, a negative 1.9, and I've got to follow it up. We're following it up to a negative 6 as my second decimal place. So a negative 1.96. Which means that this one is a negative 1.96. Well, how do I get this other one? There's a couple of different ways. Again, remembering that this is symmetric, so where I fold it over upon itself, I should get the same z value, just one with positive, one with negative. Another way is this 95% in here is the same thing as 0.95. If I take 0.95 plus this portion, a 0.0250, and if I add these together, I get 0.9750. That is everything to the left here. So let's go over here and look at our chart. And I want a 0.9750. Okay, so I'm following down 0.9. Okay, we're somewhere in here. 0.97. Right here. 0.9750. I'm going to follow it out. Okay, that's a 1.9. And I'm going to follow it up to a 6. It's the positive version of this. So my critical value here is a 1.96. These values are the same because we're wanting that middle portion. So they're going to cut off the same amount on both sides. So when you're looking at finding confidence intervals, you really need to find the actual critical value so that we can look for that margin of error. When we look for the margin of error, it is our critical value times the standard error. Recall that the standard error was our standard deviation divided by the square root of n. So we're going to multiply that by our z. That gives us our margin of error. That's how much we add or subtract from the mean to get our confidence interval. So our confidence interval is actually going to look like mean minus our margin of error, which is z times sigma divided by the square root of n. We're saying that the population mean is between subtracting that value and adding that margin of error. So our actual confidence interval is this entire thing. So I'll get that the population mean is between a number here and a number here. For our common z-scores, our common critical values, we're going to use, for 90% confidence, we're going to use a 1.645. For a 95%, like you just saw, we're going to use a 1.96. And I don't have to worry about the sign, because notice a negative z and a positive z. That's already taken into account for our formula. 98% confidence is 2.326, and a 99% confidence is a 2.576. Now you'll notice these 7 6s and everything else. These are going to be actually given to you, so you don't actually have to be able to find all of them. Now sometimes we will. Say that we want to find the critical value, alpha divided by 2. Alpha divided by 2 is that leftover, how much we have remaining, divided by 2. We want to divide it by 2 because remember that there's 2 tails. Let's scroll back up. This would be alpha divided by 2 in here. So we have this amount left over, and we're dividing it by 2 because we want it on each side. That's all that alpha divided by 2 means. It doesn't mean actually calculate something for the most part. It just means take the remainder, the alpha, the amount in the tails, and divide it by 2. We want to find the critical value, z alpha divided by 2, for an 85% confidence interval. Well, that's not one of our normal ones up there. And so we're going to put 85% here in the center, which is 0.85. And we're going to cut off some on both sides. To find the critical values, I'm going to have to take 1 minus 0.85 and divide that by 2. When I divide it by 2, the reason I'm dividing it by 2 is because I have 2 tails. And I get 0.0750. 0.0750. So this is the amount in our shaded area, our little tails. So we're going to come back over here, and I'm going to get rid of this from the previous values. And I'll get rid of it here as well, so that I don't confuse you on where I got some of these numbers. And so we needed to look up a 0.0750 in the center of the chart. So I'm looking it up here. So 0.07 is going to be somewhere around here. 0.750. Oh, I don't have exactly 0.0750. I have 0.0749 and 0.0735. I don't have a 5. So what we do is we go to the one that it's closest to. Because recall, we're looking up a 0.0750. This one is 1 value away, whereas this one is about 15 values away. So we want to use the 0.0749. I'm going to follow this out to find its z. So a negative 1.4, I got to follow it up to find the hundredths place, and that's a 4. So a negative 1.44 and a positive 1.44. So the critical value that we use, z alpha divided by 2, is a 1.44. You'll notice that we're using the absolute value of this. And that's what we're going to work with, is actually the absolute value, because look back up at your formula. Here's the negative, here's the positive. Those are already taken into account. So I'd like for you to try finding some of the critical values, and then let me know if you have any questions.